The broadcast is now starting. All attendees are in listen-only mode.
Good afternoon, everybody. We'll start the presentation in 2 minutes. We're still waiting for some more people to arrive.
Hi, Ronald.
Hi, Erika.
Finally. Okay. Sorry.
Yeah, we started the broadcast. And maybe people should mute the microphone if they are not talking, because there's some echo.
Okay.
So let's wait a little bit more, 1 more minute. Okay, let's begin. So the screen that you now see is a bit, it's not ideal, but the GoToWebinar system doesn't seem to allow full screen. Therefore, I hope you can forgive me that you see the window like this. I hope it is still readable. If not, please leave a message in the chat window. So if you go to your control panel, you have a chat box, and there you can talk to me or the presenters. And that will also be used for questions and to raise questions, which we will try to answer at the end of the webinar. So, so today we are going to talk about the societal challenge health, which is part of the Big Data Europe project. And we'll give you some insights into how the project started and why this pilot is relevant for the project as a whole. The planning is as follows. So we'll give a short overview of Big Data Europe. Then I will do that. Then Stian Soyland Reyes and Bryn Williams-Jones are going to talk about Open PHACTS. Then Erika Pauwels and Aart Verstede from Tenforce will give you an overview of the current state of the infrastructure being developed for the project. And then Stian takes over and shows a bit more about the Open PHACTS Docker, which is the instantiation of the first pilot. Here are the people that are going to talk today. So Big Data Europe, what is it about? So we can basically say there are three goals. First, there is, of course, the big data. And one major part of this project is that lots of data needs to be integrated in order to solve the business or the goals for the various pilots. So Open PHACTS is a good example where there is data from various heterogeneous sources. They have different formats and different semantics, different identifiers. And that has to be integrated. So in that sense, it's already the variety of the data makes it big data. Another goal of this project is to develop software of components and an infrastructure that makes it easy for people to develop their own pilots or their own systems on top of it. So we are building generic components, to manuals, and present use cases, which they then can compare with their own. And then they can select those which are recommended by these pilot examples. So they're kind of templates for your own business cases. And last but not least, this project is also very focused on gathering a community, and especially in Europe, on the whole topic on big data related to the 7 societal challenges which are identified by the Horizon 2020 goals. So here are them, they are in an overview. So today we will cover the health societal challenge, which is mostly on heterogeneous data linking and integration. And the other ones, I will just quickly go over them. We have food and agriculture, and we are going to make a pilot on wine, on the wine science, on grapes, and they have all kinds of properties, the soil conditions and the genotypes and the phenotypes. It's quite related to the health case because there's a lot of heterogeneous scientific data that has to be integrated and linked. Then we have energy, that is about monitoring and stream processing. So there are big windmills, turbines, they have lots of sensor data, and they need to be monitored. So that is real stream, big data stream processing. Fourth one, transport. There's to predict the traffic jams and the flow in the cities. There are all kinds of sensors in the roads. So this one is covered by people in Athens, in Greece. And they try to do analyze the streams of sensor networks to make predictions on the traffic. Fifth one, climate. There are all these models, climate models, and if you have a specific use case for these climate models, these models need to be recomputed and to be how can you say, transformed into data for your case. And that is a big data problem because it's a lot of data, these climate models, terabytes of information. So there needs to be a lot of processing power to transform these models into for your situation. Social sciences, that is information about the government spending data. In this case, the first pilot from all kinds of governments, they have spending data and you want to make analysis over it. And the last one is security. We have SATSEN, they have a satellite, access to a satellite, making pictures every day of the whole world. And they want to compare pictures between different periods to discover changes in that location. You can think of maybe a refugee camp that suddenly came at a certain location. And that is a lot of CPU power to do all that work. There are a lot of partners in our project from various countries. Here's an overview. I will not go over them. And at the end of this session, we will have a question answer session moment. If you have any questions, please leave them in the chat box, and we will answer them at the end of this webinar. Okay. Now, I would like to give the screen to Bryn, and Bryn is going to talk about Open PHACTS. See.
Great, thanks Ronald. I shall wait for the button to appear and click it. Hello to everyone that's listening. Here we are. Cool. So I'm just going to talk a little bit of background about Open PHACTS Foundation and Open PHACTS and where it's come from. I'm quite merrily will point out that all the technical questions, I will be the last person to answer those, but fortunately that's what Stian is going to go into a little later. But just by introduction for what we're doing with data in the healthcare space in this project, a bit of background on Open PHACTS, what it is and where it came from. And really the reason why we went to the trouble of building the infrastructure that we did is because it's really quite hard for people to ask questions of scientific data in the biomedical domain. The data it comes from lots of different places. It's not very well integrated. There's a general lack of standards, and trying to ask some simple questions about a paper you're reading in this case, where you're trying to think about what data is there, what's the drug target, is there anything similar, all those kind of standard questions that people who wear a lab coat for a living have. It's really hard to get some of that data from one place to really answer those questions, unless you are significantly skilled in the domain, which a lot of people aren't. In this case, the Open PHACTS project, as it was then, came about from discussions between different pharma companies, and really it's around how do people use the public data that is out there in the public infrastructure, from publications, from sources of gene and disease and target information from repositories, and most companies take those databases, download them, put them behind the firewall, do some integration and do data analysis on that at the kind of final stage downstream. And if you look around how companies are using this data, lots of companies are doing more or less the same thing with more or less the same data for more or less the same reason, and it's massively duplicative and wasteful. So the idea for Open PHACTS came about originally as an IMI project, which is the world's largest public-private partnership in health research, 2.5 billion euros worth of commission money and 2.5 million euros worth of drug discovery industry in-kind resources, a public-private partnership. Hesitate to add that our project didn't have 5 billion euros. That would have been very nice, but we ran for 5 years with about 20 million euros worth of infrastructure building in there. And really what the mission was to integrate these various research biomedical data resources in a single open and free access point and make it sustainable in the longer term. And that's what the Open PHACTS Foundation is, and we are continuing to do. Really, there's a few things to tackle in this space that speak to big data and the importance of why we're doing all this. And really, naming and standards in biomedical science is a nightmare. There are 3 industries represented on this particular slide. 2 of them don't have an argument about what pieces of what a wing is called, or how to get software to work on your smartphone when you're in different countries. In biomedical science, we love to get very confusing about namespace, call the same things different things. Aligning all that data, integrating it at scale is a significant challenge, and that's one of the things that we really focused on, because to answer the questions that people have, again in early research, and we're starting to move this through into translational medicine and in clinical medicine, this tend to be reasonably simple questions about a drug or about a disease or about a drug target or a pathway. And finding the answer to those is really challenging, and they can be in any of these places. And how do you know where to look? How do you keep the expertise in that? Do you remember what the tables are? How do you actually remember what is in some of these things and get them all out and answer them, when really what you're trying to do is cure a disease or do some research into fundamental science? It might not be the best place to do that. So hopefully Open PHACTS takes a lot of that, puts it together in one place, in a hopefully sensible place, so that you can answer some questions with confidence on properly tightly integrated data. I'm not going to go into a huge amount about what's there, but it's the way that we try and manage some of the complexity in that space. And you know, some of the bits of infrastructure and the key bits, I'm sure that Stian will go into a little later when we get to talking about the Docker. And really, you know, part of this was an experiment ourselves for how we could you know, build semantic infrastructure to do drug discovery data services, and also start to think about how people might use that, whether it's, you know, openly in the cloud, whether people want their own instance, how we move that about. And this coincides with our interest in this project and our role in Big Data Europe for how to you know, port our infrastructure into different big data technologies. You know, can we use what we already have? How plug and play are some of the technologies that are underneath this? So that was, you know, all I was going to say by way of introduction. I know it's quite a quick whistle through, but I think certainly from, you know, the perspective of biomedical data in Big Data Europe is how do we cope with the variety of data and the integration that we need to do to be able to still answer those business questions, which are all about finding, you know, new cures for disease. So I think I need to pass the presenter on. Ronald, is it who's next? Sorry.
Yes, so Stian is next. Thank
Great.
you for the nice introduction on Open PHACTS. And again, people, if you have questions, please leave them in the message box in your panel.
Okay, so I'm going to be presenting more about the architecture behind Open PHACTS. We'll do the Docker in the second half, but this first, to understand that, we need to know a bit more about the architecture behind it. So as we heard, Open PHACTS is bringing together all the different data sources, many of which you will have already heard about. And we expose them as a public API. You can register, you can get documentations about the inputs, outputs, and I think there's at least 30 different methods you can call there. You can ask, as a developer, you can ask for them in any kind of format that you like. You can get your JSON, you can get some XML, you can even ask for the RDF if you actually still really like RDF. But many people just want to see the data without actually looking at the structure. So we've made the Open PHACTS Explorer, which uses this API, but presents this more for the users. I'm just going to try to use it now to search for, if I can spell it correctly. Okay. And you can see, while it's actually doing the API calls now from the web client, so there's no intermediate thing. It's using normal REST calls to do that. And you can see, if you click to show problems, you can see where the different data sources come from. You can see we have some calculated properties, we have some bits from Uniport, Drug Bank, and so on. And you can do, will be doing additional API calls in the back end for looking up pharmacology and so on. So this is just one example of what you could do with the API calls, but there's much more you can do, and we have lots of workflows that also explores the 20 science questions in detail that you can use as examples. But what is the architecture behind this all? Well, we have to put it all together. So at the top, we have authentication. You need to register to get access. This is just authentication your API key. Then we have an API layer, which you can present to different formats that you saw. This is backed by a series of queries. Each API call is basically a big query that selects different properties from lots of different data sources. Now, these are stored in a triple store underneath here. That's the Virtuoso RDF triple store. So we have loaded all the public data sources into one big triple store, but kept separate in different graphs, and that's how we can do the queries. We have a caching layer to speed up. As you saw, I got really quick response to this pharmacology responses here, but if you do brand new ones, it might take a bit longer the first time because there's a cache to help speed up commonly asked things. Now, the magic thing, in a way, is that these different graphs, as Brett mentioned, they don't use the same identifiers, right? So you can't just write a one single query to go across them because they're not linked. So that's why we have the identity mapping piece in the lower corner here, and that's loaded with lots of link sets. Some we should have derived from the graphs, and others we have calculated, and that brings the identifiers together. So what the API does is it knows for each source what kind of identifier do I need, and it asks the identifier mapping to give you that link back, and then it forms a query that is then sent down to the triple star, and then there's transformations in the end to the different formats that you asked for. A couple of API calls basically just forward out to other services like the structure search and the text search. Those are maintained separately because they have different databases. So when we load data in, if you could think of Campbell and Uniportzone coming in, there's basically 3 different places they can be loaded in. There's the identity mapping service in the bottom, which keeps the links between them all. That's the most important one, because otherwise it's not connected to anything else. So if you add a new source, that's the minimum you can do. If you've done that, now those identifiers are recognized, and you can use them in all the other queries, even if that data is not described with that identifier. Then if you can load the RDF data into the store, but if you do that, you probably want to add it to the query so it's exposed in the API. And then finally, we have a chemical structure search service, which recognizes the compounds and finds out if they're the same and calculates some properties. And this is kind of like a fallback when you haven't got a link, but you can still see it is the same compound. It's got basically the same smile string and so on. We can calculate equality in that sense. So that's it for the architecture. The rest will be Docker, but we'll do that in the second half, I think.
Thank you very much, Stian. So now I would like to give the floor to Erika and Aad. Make presenter. There you go. Erika, the floor is yours.
Right. So I'll be talking. I'm here together with Erika, and I'm Aad of the SU. We will be presenting the base architecture. Looking at the base architecture, just waiting a second till it full screens, but that will happen in a second, I suppose. Right, so while we're full screening, which will happen in a second, or we present it like this, there's a certain set of goals that we have with the platform. The idea would be that the platform is as cheap as possible to use. So that means, in a more businessy terms, it means to have a low total cost of ownership. Now, a low total cost of ownership, that essentially means that it needs to be easy to install, it needs to be easy to run, to maintain, but also to get started with big data. Because some of the people, mostly most of them, won't have that much experience with it yet. From that point on, given each of the societal challenges which have been briefly introduced, we notice that they have widely varying use cases. It may be that you have a lot of data, it may be that it changes a lot, it may be that you have some variety in there, or with Open PHACTS being a rather extreme case, it's variety to the extreme. And the platform as itself as a whole should cater for those. We also noticed within a certain set of technologies, within one set of limitations, the set of technologies you're supposed to use can vary a lot. When we started this project, Flink was basically nothing. It had virtually no documentation whatsoever, but now it's a real contender. So we want to support it now. Given that that is something you want to do, then you'll notice that either companies have something internally running which also needs to be supported, needs to be integrated or running on the same platform, or at least communicate with it easily. And even without, technologies weren't always big data technologies. This is an image, I think, from 2015 showing the big data space that was common then. Now, the big data space that was common then is not the same one here anymore. Each of those boxes contain about 5 items. or more of them. It's not really possible for us to support all of them. However, should you choose to use one, then preferably the platform as a whole should support it. Now, why would we want all of this? Well, it is big data, and big data is classified as being the 4 V's, is what it's called here. You have volume, which means you have too much data. It doesn't fit on your hard drive. You have too much velocity, being it changes too often. A regular algorithm doesn't really cut it. It may be variety, being the data is not really structured in one way. It's a lot of different types of data. And veracity, you may not even know whether the data you have is true. We had to build a platform that would encompass all of these. And an initial view would be that you would solve something for variety, for instance, something for volume, something for velocity. But it turns out that no one has just that problem. So we're building a platform that solves potentially all of them, but given that you select the right other components. The platform that we envisioned from a high-level point of view looks a bit like this. We use Docker Swarm, Docker Swarm being the technology that will scale or will say what needs to run where. Now, Docker Swarm runs on a certain set of nodes, which are these bottom things. A node in real life is going to be a computer. It may be a computer that is running in your office. It may be a computer that is running on the cloud. It may be on your own cloud infrastructure. That's all open. It runs just about everywhere in theory. And so far, we haven't noticed many limitations yet. On top of that Docker Swarm, we will run something called a Docker Compose here. These are pipelines, as we call them. A pipeline is something that solves a tangible problem for you. A tangible problem can, for instance, be the Open PHACTS stack, which contains everything to be able to answer API calls. Each of these applications in there, those are specific technologies which you may use. For instance, one may be a big data computation technology. That could be Spark, or if you're very modern, it could be Flink. One could be HDFS, being something to store your data across various nodes. And all of that is just, so again, is combined within a Docker Compose. Looking at it like a somewhat practical example, it's a theoretical one, so don't judge me if some of the lines are wrong. What you see here is there's a for store, which is a semantic store. It's a triple store. There is Flink running with a bunch of slave nodes and then 2 master nodes. There is HDFS running, again with a set of nodes, and there is Spark running. This could be a viable pipeline in which, for instance, we gather some widely varying data from a triple store, then compute some indexes over it using Flink, store that on HDFS, and later on process it using some prediction algorithms in Spark. If you then visualize it using the previous image, this may look a bit more like this. In this example, you see that we've put HDFS in your application, Spark is in there, Flink, and Forestore. Indeed, you have a lot more nodes running on it, but from a high-level point of view, the way people will think about it, it's sufficient to know this technology runs on it, and it runs on a certain set of nodes. You see 2 extra things here. There's the semantic big data, and there is a support layer. The semantic big data thing, I'll discuss it more concretely in a second, is basically some set of technologies which we add in order to make big data processing possible over semantic content. That's something that currently doesn't really exist in the industry. The support layer is even more pragmatic than that one. For a previous one, we noticed that there are certain parties or entities, a lot of them, that need it. For the second one, the support layer, it's merely that although Docker Swarm will probably have a solution for this in the future, right now it doesn't. And we want to have a solution for it. For instance, to give you an example, there is something needed in order to say what will start running at which time. We'll go more in depth in it, but that sort of thing. It may also be something that provides you with an integrated view. This system, though, as you see, all these layers run on that same Docker Swarm. So that means that if you install that system, then everything else will run, and you'll be able to upgrade it. Important here, within your application, is each of the components which you drop in there is a specific version of that component. So it's not only the configuration of that component, it is a certain set of binaries that will run on your machine. If your whole cluster crashes and you set it up again, next month, In the next month, that whole thing will be running exactly the same. There will be no differences. That greatly lowers maintenance costs, because once a pipeline is running, as long as it doesn't need changes, it really doesn't need changes. It just keeps working. That also means that these two sets, the support layer and the semantic big data layer, that these components can evolve based on your specific needs. Let's dive into the semantic big data layer a bit. It's very much ongoing research, but it is important that we mention it, mainly because we may find interesting partners for it. The semantic data lake is one of the two bigger things that is happening here. The semantic data lake is the idea that rather than having just your data lake as is commonly known right now, we will semantify it. We will make it that the semantics of each of the files within the data lake are known. Essentially, there's a bit of a risk with a data lake, being that you encounter a data swamp, which is you've dumped all your data in there, but you can't really access it. We're trying to solve that to some extent. The second is a Samza stack, which would allow big data analytics on a very large semantic graph. It's also something that's currently not really feasible, at least to some extent, and we're trying to fix that because we do notice that some entities have a problem with that. The support layer, very pragmatic. Some pictures will arrive later in this short presentation. There's a Swarm UI which allows you to launch and install pipelines, which essentially means that we make it easy to a clicky user interface to launch a particular application. There's a pipeline daemon and monitor, which is something that determines the order in which certain components need to execute. In this previous example, for instance, we'd first make the Flink computation, get data from ForStore, and dump it into HDFS before Spark can do computations on HDFS. So it's extremely pragmatic and simple. Lastly, there's the integrator UI, which presents you a nice dashboard of a unified interface so that it's all a bit clear as an end user what is going on in the system. Again, it looks a bit like this once the architecture is running from a high-level view. More pragmatically, looking at how we support various entities, we look at 4 different main actors, and it needs to be simple for each of these actors. The first actor is going to be the setup, being the person that installs the system. That may be the developer that needs to install it, or it may be your sysadmin that needs to install this platform on your local cluster. We made extensive installation guides. Well, they're not that extensive, but the only reason why they're not is because it's very simple to install a platform. You have 2 ways of installing it. You can do it raw on the machine itself, or you can do it using Docker Machine, which essentially is the best supported system. Second actor that we are supporting are the developers. This is, of course, my personal interest the most. This is the person that will implement a pipeline. So this is, to some extent, the bulk of the development work that will happen. We support in 4 different ways. Essentially, what that person will do is they'll build a high-level picture of a solution, being a Docker Compose file. It's just a simple text file, essentially, that describes which components are where and how they link to each other. Second, you may have common components that you use. The common components are things like, for instance, Spark. And although Spark is something standard, you will need to include your algorithm. So what we do is we make it so that everything will go automatic except the writing of that specific algorithm. For new components, we give you a tiny little virtual machine, it's a Docker image essentially, where you can drop in your custom component. You can share this whole thing just on Git for the pipeline and publish the components on Docker Hub, or you can do this privately as well, so it's not that you're tied into our system or something. If you do it a bit more graphically, it means that you get this picture in which this is the pipeline that is published online on GitHub. You have various set of applications that are described in it, and some of them may just be extensions of a standard system. Some of them may just be a default, like a Spark worker. You don't need anything custom, just add it there. Or it may be something that is a custom in-house application. Thirdly, there's a deployment. You have received a pipeline. You know you want to run it. How do you deploy it? Well, so far it was a manual process that you had to type in some very simple command, but still it was something you had to type in. We've automated that to some extent using a Swarm UI. Right now you have a clicky interface in which you can say, this is the pipeline I want to have, a particular user can add that, and then you can run it. When you try to run it, it looks a bit like this. Running it, you can see these numbers. Well, maybe the resolution isn't high enough, but these are numbers. You can essentially scale up various components. Scaling it up means when you notice that a certain computation is too slow, you can allocate more resources to it. That's the essence of it. Then you have the monitoring. The system has started. Your end user, or maybe you yourself, the one that has deployed it, may want to say, I want to look at what's happening. Well, you can, of course. Some of it is through that same user interface in which you can say, I need more resource for a particular component. You can also monitor the output logs. And monitoring is an extensive thing that we're still looking into. But you can essentially monitor what the direct output is of a component. You can also have an integrated, and you always have this, an integrated user interface. This integrated user interface provides you specific visualizations of specific components. The developer, from the previous step, decides which things are visible here, but it may be a Spark dashboard that shows you which workers are connected. It may be an AGFS overview showing how much data is being used, that sort of information. It also shows you the the workflow UI. The workflow UI shows you various steps that need to happen. And in these steps, you can see how far you are. This one in particular, for instance, shows that it's first setting up AGFS, then it's setting up Spark. And once these are done, it requires you to populate AGFS with the data over which you want to run your computations. This is a manual step. So this workflow UI is both something that allows you to monitor how far things are, as well as allow you to see what still needs to be done from you, from an end user. Monitoring, though, is certainly an active topic. There's a bunch of very interesting things which are possible there, and it's very hard to build something that is broad and works across everything. We have both a very generic thing which works for the logs, which allows you to have some insights. We have something that allows you to do the scaling. We have something that, should you want to do it, you have very extensive ways of building user interfaces that shows particular outputs. But there's more interesting things to be done. Maybe we can visualize the logs using Kibana. Maybe we can combine the logs so that you have a larger overview. You may want to monitor the particular load of a node, though in practice we're now relying on the vendors of the cloud platforms to offer us that. We may want to provide auto-scheduling, which automatically schedules more nodes. This was a high-level overview of this platform. It is used in practice as we speak, of course, because we have the societal challenges. We also use it internally even. It's rather easy to get started, but it is still improving as we speak. A high-level picture is this one. Should you have more questions?
I think something happened with the sound.
Yes?
Sorry, Ad. I think there was a problem with the sound, either on my side or on yours. But okay, it's back. Thank you very much for this nice overview. I learned a lot again as well. So let's now move to Stian again, and he will give us more information about the Open PHACTS Docker.
Okay, hang on. Here, I hope you can see that. So I guess, thank you, Erica, for that presentation. I think we need, I didn't quite know how much detail we're going to present Docker. Maybe just as a brief introduction what Docker is, because maybe we should just remind ourselves what that is. Basically, it's a Linux container technology. You can think of it almost like a virtual machine, or kind of like, what if you could run multiple Linux kernels in the same machine? So you can't see each other, but you can have multiple file system, multiple network points, and so on. Now, Docker organizes all of this in a very easy way to deploy and manage, where you have a container, which is an instance started from an image. An image downloaded from the Docker Hub, or you make it yourself, based on our Docker file. And this is a layer-based recipe. You can use existing images, like you say, from Spark, and then add some files and change this config, and now you have your own little image. Now, this has led to the philosophy in Docker where you have one service, one image, and then you have microservices. And you saw in the previous talk how that means you can scale up each individual service separately, and you can upgrade them at will separately, and so on. So basically, it's your cloud's best friend. Because if you remember when maybe you were first trying to use the cloud, you just get a totally blank machine, and now you have to install everything. Well, Docker solves that for you. And so you get scalability, you get reproducibility, and still you can retain customizability, if that even is a word. All right, so let's look at OpenFACTS. So if you remember from the architecture diagram, there's different kinds of components there. So we basically made Docker images for those that are our own software, and we use the existing ones where they exist. So here you can see we have Explorer, Identity Mapping Service, and a couple of other things. Now those are in the Docker Hub. And you can put them together like this, and then it's basically the same as the architecture diagram before. We have the Explorer that uses the API, backed by Virtuoso, the RDF store. IMS is the Identity Mapping Service, which loads up from MySQL, and then the cache is just staying on the side of the API there. And then in Docker, sometimes you want to move the data outside the actual container, both for efficiency and space reasoning, but also to make it easier to upgrade. So here, the data for the Virtuoso is separate blue box in the bottom, and similar to MySQL with the link set in the bottom. And that means we now get a problem with how do we get data into there. And I'll show you more about that in a minute, but basically we have a data side for populating that. Now, how do we start all of this? Well, Docker Compose, as we heard, it lets you say which images do we download, which data volumes are we going to use, and which network ports are we going to expose, because maybe you don't want to expose everything to your to the world, but some of them you want to expose. And these containers can be linked together. Basically, they see each other as virtual hosts, so they can talk to each other. And then to get a single point to just start and stop all of the containers. And Docker Swarm is basically Docker Compose on multiple nodes. And there's also something called Docker Machine, which allows you to do this kind of in between and spin up virtual machines and so on. The Docker guys have made lots of cool tools for this, so we're just jumping on the bandwagon and using it. Now, Docker Compose is a YAML configuration file. We have different sections, one for each container. So it's quite straightforward to make. So basically, we have the Explorer using a certain image, expose a certain port, link to an API, and that's the next section, and so on. So each of the boxes you saw before is basically just a section in a config file. Now, I mentioned data. There's one issue here, and that is big data depends on the order who you're talking to. For Docker, big data seems to trip in at around 10 gigabytes. This might change over time, but basically it says an image size shouldn't be more than 10 gigabytes. Then they will refuse to host it in the Docker Hub, and you'll have to do all kind of workarounds. So as the OpenFACTS data put together is about 30 gigs compressed. When you installed it and it's ready to run, 200. Now, it's not really big in today's standard, but it still is non-trivial, right? You can't just do a single download and hope for the best and hope that it didn't go wrong. So our solution is that we've added additional containers to do the staging of the data. They download the data from our data side. They verify some checksums and the consistency before they then import them into the RDF store and into the MySQL store. And we have a data repository for OpenFACTS. This is where you can go. There's some data openfacts.org, and you can register to get access to the raw data if that's what you want to do. If you just want to install it, you can just click the install button, and you'll get to see how you can run the Docker install that I'm talking about now. You can also use the API directly, but of course then you don't need to install anything. Now, if you do register, you get to see the individual data sets that we have used. Now, these are not our data sets. Mostly they are imported from elsewhere, like from Uniport, Campbell, and so on. But we kind of re-expose them because each OpenFACTS version is based on a particular version of each of the other data sets. And then additionally, we have the link sets, which we have formed between them. And then there's metadata and provenance around these. And to simplify installation, we have also this kind of like merged ones. Like if you see this all right here, there's a MySQL SQL dump. That's one big SQL statement that loads up all of the link sets in one go. So that is for efficiency reasons for the Docker install, because otherwise you might have to wait a couple of days to do all the parsing. So instead, if you can do it in half an hour on a fast machine, that's always good. So I think you should try it. You don't need that much of a machine. You just need a few hundred gigs of disk space, maybe 16 gigs of RAM, and a couple of CPU cores. Ideally, of course, if you want to put in production like we have, you need a bit more, right? Maybe like 60, 100 gigs of RAM if you want lots of users. But if it's just for you, you can do just a decent under-the-desk server should work fine. Just make sure you have the latest Docker and a latest Linux. But I'm just telling you, don't jump ahead and do too many assumptions, because we've seen that. We've written a tutorial on GitHub. If you see here, GitHub.com, Open PHACTS Docker. If you follow that step by step, it should work. But if you start doing lots of deviation from the beginning, then you'll have to debug it yourself, right? And you're just going to test on Windows and Mac. Well, it does work, but you have to make sure the details are right, that you have enough disk and memory to the virtual machine the Docker then starts up. Now, I think we could move to using Docker machine to automate that bit. And also, if you're behind a firewall, there might be a few different things you have to change depending on what is your requirements. But there shouldn't be any worry in trying this out, because Docker is containerized after all. So if it goes wrong, just wipe it out, and it doesn't affect the rest of your machine. So how do you do it? Well, if you look at the tutorial, you'll see the step-by-steps you'll have to do. Rather than the one command to run Docker compose, we do it we break it down, kind of like the workflow you saw before from Erica, because you want to make sure that you have downloaded all the data, you have got all the software, rather than just stop in the middle because you run out of disk space or something. So the first step is to download all the data. This just downloads all the Docker images for the different services. This is done in parallel, so it's usually quite fast. Then you need to get the data, and this can take a while because it depends on your network connection and so on. We have some different measures to speed it up, but at the moment they're kind of disabled because of some HTTPS issue. But that's not important. But it will download all the data from our data side. If you have firewall that blocks it, then you would have to do this step manually. But generally, this will just download all the data and then import it in. And you can look at the log files. When it says it has loading completed, then you can start the services. Now, this is the kind of where the normal Docker routine has to be kind of a bit more handheld, because if you start up everything too early, the data is not there and the services get a bit confused. So that's why you have to do this as a pre-step. Once you have loaded all the data, you don't need to do this anymore. And then you start the services, and if you want all the details, you can ask for the log files and get lots of pretty colors. And as long as you don't get lots of big stack traces falling over your screen, then it should be working. But this is basically what we will ask you for. If it doesn't work, it will be something in here to look at. But you can see the different services are now up and running, and that means you can start access them. Now, by default, we just expose them on 4 different ports, starting 3001, 3002, and so on. You can change this. But if it's all just started up, then you will get the 3001, you will get the Explorer, and this is actually running from an old MacBook Pro in Manchester. So, so you can see it's still doing the search here, and you can look it up, and it's doing the search, and it looks pretty much the same as the production instance. You will find that the drug bank data is missing, but that is because it is that's a commercial data. Well, this only loads the non-commercial data by default, but generally they will look exactly the same as in production. If you do 3002 instead, you have the API access point. Now, the documentation is all in there, but it's not as nicely formatted as on the web page for the production instance, but you can just use the same URIs and then just change the host name. And you can see here you have the same documentations for all the different methods that you can call. And that will then be running on your local instance. If you want to go real hardcore tech, there's the Sparkle endpoint where you're left on your own. You have to find identifiers yourself and go do your queries. But it's there for you to have fun with. You might want to block this because if you want a nasty query, then you could of course block it for everyone else. Just like if you expose the SQL to the database. Now here is the identity mapping service. So this could also be useful for looking up identifiers. So you can look up different kind of identifiers in here, and then you can see what are the other identifiers that they map to. Now, what is the next for Open PHACTS as Docker? Well, one thing we want to work more on is the data staging to make that customized. I mentioned this thing with non-commercial and commercial, and that's something that's come up in the latest Open PHACTS release. Depending on which user you are, you might not be able to use all the data. For instance, Drug Bank has a non-commercial use only license, so you would have to explicitly enable that. So we will need some kind of options for kind of filling in different kinds of data here. One thing that is interesting to look at is to take this microservices step a bit further, because if you look deeply at many of the queries we run, basically they can be broken down into one query for Uniport, another query for Campbell, and so on, and that could in theory be multiple microservices that don't need to run on the same machine. So that could in theory be broken apart, but then of course you would need a new thing that merges them together again as a final endpoint. But this could be an interesting way to scale up the big data sets. You don't need to scale up the small ones. Also to test upgrades, you can have different kind of versions of the data set at the same time. But still you need to do the identity mapping because the different data sets have different kind of identifiers. I work in the BioExcel project, and one thing we're looking at there is to build workflow blocks. And in particular, we want to use Open PHACTS, but use it locally using Docker, and then spin it up on demand in a way. So if you have a workflow that happens to use Open PHACTS, spin up your own instance, and then shut it down afterwards. And obviously, you don't want to do the data loading again and again for there, so you can use that this space is cheap once you know where you're going to run it, and do lots of things there. And again, you have the scalability and reproducibility. If you want to be stuck with an old version of Open PHACTS because you don't want to upgrade your workflow, this is already a case that people don't want to upgrade, then that shouldn't be a problem as long as you have installed your own Open PHACTS. And we want to expose Open PHACTS services as tools in the bio.tools service registry, because I don't see any reason why they couldn't, even though they're not command line tools, but they are still something you can install and run. Customization is a big thing because people want to add their own data, particularly commercial actors want to add their secret in-house data with all the research and mix it in. Academics want to try the latest data, they want to expand the data. So improving the Docker install to make this easier is a major point. Or is that through more tooling, through more documentation, or more training? I think it's a bit of all of these things. And we have room for working on all of those things. So that's it for me. So any feedback, you can raise issues directly in GitHub if you can't get it installed to work. With Open PHACTS, generally, you can ask in the Open PHACTS support forum. And for BioExcel, we also have a forum where you can ask any kind of question independent of technologies. Yeah, so that's it for me.
Thank you, Stian, for your excellent presentation. So we now are at the end of our webinar, and we go into the question and answer session. Are there any questions from the attendees at the moment? Please type it in the question box. You can also just say, I can also make the audio available, So if you want to verbally express your question, it's possible. Just leave again a message in the question box, and I will make you the speaker. I have one question for you, Stian. So this IMS service is seems to be quite important in the whole Open Facts infrastructure, where the identity problem is one of the biggest one in case you want to integrate data. For me, it is kind of clear if you have RDF data that you just import it into the database that you have. So in this case, you have Virtuoso, but currently I know that we are investigating other RDF stores which are more scalable, like Forstore. But this IMS that runs on the MySQL database. So for the audience, it's maybe interesting to know how easy it is if you have your own custom link sets, how to deal with those.
It's quite easy to add the link set. You just add, there's a command you run to load them up, and you need to have the link set at the file or URI, and you make a minimal void file where you say what you're linking from and to, and then you say why you're linking them together. Because the reason why you link them together is important for the IMS, because it calculates transitives as well. And sometimes you don't want to do the transitive. You can't just do like our same as A equals B equals C, because sometimes you then do stupid things where you say one gene is equal to a protein that is equal to a gene, and suddenly you said that two different genes are the same, which clearly they're not. So one thing that we have in IMS is also this something called lenses, where you can kind of choose the blurriness you want to have and the quality, and that's it's something we've been mainly experimenting with, because it's one that is a bit hard to document, but basically you can enable a broader search, which then is reflected in all the API calls, and having the IMS allows you to do that. But once you've kind of settled with what kind of equalities you want to have, we already know that this link set is linked to this other one and so on. There's nothing saying we couldn't pre-calculate it and just add it to the RDF store. But even sometimes we have several identifiers within the same service, but they have different namespaces. So that's another issue in RDF, where people say just Uniprot. For instance, there's www.uniprot.org/p something something, or there's perl.uniprot/blah blah blah something. And different sources use different ones. So you will need to have a normalization step to link these things together. But sometimes it's not a one-to-one, and again, this allows us to have that flexibility. But it's something that is possible to change, right? Because once you've restricted down exactly what you want to calculate, you know which queries you're going to run, you don't need to calculate any time. But that said, there's no issues with scalability, because MySQL is really fast in just looking up A to B. Is not particularly complicated. So we've never had an issue where the IMS is slowing down anything. But it does mean that there's an additional step in adding a new data source. But there would, in a way, need to be that anyway, unless you have already added those equality somewhere in your new data set so that you could use that in your query.
Okay. Thank you. I got a question from Ian Harrow. And his question is, how many external groups have installed a Docker VM to date? I'm not sure if I completely understand the question, so maybe I will unmute you, Ian, and please go ahead. You are now having the microphone. Okay, maybe I overpowered you. Because I don't completely understand.
Can you hear me now?
Oh, yes, perfect. Yeah, please go ahead.
Oh, good. It's basically to understand how many external groups have installed the Docker VM images of Open PHACTS as Stian has described. Is it early days, or is this a mature process, and it all goes very smoothly and there are no problems?
It's not super smoothly because things are moving along. Docker technology keeps changing, and people's hardware is very different, and so on. But it's not like people haven't used it. I would say it's somewhere between 6 and 10 different people. We don't have exact numbers because we don't require anything particular for people to do it, but of course we could look at the download statistics for the data loading to maybe crunch some numbers and see.
Okay, thanks.
Yes, and it's important to note that for the BigDataEurope project, so we are now currently in the first stage of the development of the pilots, and there are 3 stages during the whole of the duration of the project. And this is quite a complicated project because you have all these 7 challenges, and we have all this new technology. We have to align everybody with the same vocabulary so that we can talk to each other in such a large project. So the first cycle of pilot development is of course the most difficult one in terms of getting something that is available and ready to use for people outside of the project. Therefore, at this moment, it's maybe a bit too early to share. Of course, you can download it. It's all open. We have our own Docker repository. You can download what you want. But maybe it's a bit too early if you expect a stable version and a perfectly documented one. However, if you like, you're more than welcome to try the various things that we are developing at the moment. Did this answer your question, Ian?
Yes, thanks.
Anybody else in the audience who likes to pose a question? Okay, I had one more question, and now to Art and Erika from TenForce. I had a question: how the semantification, what that is being meant? What is semantification meaning in this context? And how is like RDF? What does that have to do with the Docker environment and the infrastructure by itself, independent from the Dockers and the pilots? Art or Erika? Are you still there?
Sorry. Yeah, can you repeat, because we were disconnected for a while. Sorry.
Okay, so the question is, what does the semantification have to do with the infrastructure? What is it and why?
It is not per se. So on the infrastructure, there are some things which we are considering, which do contain some semantics. One of the things being how you can connect various APIs, which is essentially Ronald's work, which is nice. Secondly, we notice that a lot of the questions we get from people that want to get into big data to solve their data problems within their company or other entity, that they're not really volume problems or velocity problems, but that they're mostly variety problems. And for a variety problem, a semantic model seems to help a lot. There's quite a bit of experience there. We consider it to be part of the platform in the sense that whatever we offer we try to combine the right set of technologies and we implement those things which don't exist yet in the industry. In the industry, what doesn't exist yet is a good solution for variety. So in that sense, we consider it to be part of the platform. However, like any other component of the platform, except for the base platform, of course, you're free to use it or to not use it. And for most of the things, especially that holds for the semantification or anything with semantics, you can choose a specific version that you want. So you can keep monitoring the progress that happens from a research point of view, see which things work for you, and then use them as they seem fit. I do consider it to be, and me not alone, consider it to be a rather important point of the platform because the value of it is rather high. But you can go without if you want.
Okay. Okay, thank you very much, Art and Erika. We are now 5 minutes already past the 4 o'clock point. So I suggest that we round it up. And I would like to thank all the presenters for showing their insights into the interesting stuff that we are all doing. And of course, for which we're all doing it for, the attendees to have joined this presentation. It is all being recorded and will be made available soon via the Big Data Europe blog post. So thanks again all, and I hope to see you or hear from you in the future. Goodbye.
Thank you. Bye-bye.